Section 4.4 is in many ways just a continuation of what we learned in the previous lecture. 4.4 deals with properties of definite integrals, which we already know how to solve. And let's just build on what we learned by first focusing on Theorem 5. Theorem 5 says that if you have a value C that is between A and B, and if you look at the picture here, notice that we have a value C, which is located between A and B. And it says the integral from A to B for the function with respect to x is equal to the integral from A to C for the function with respect to x plus the interval from C to B. In other words, if you were to calculate the area, let's say, under the curve from A to C, and then you were to calculate the area under the curve yet above the x-axis from C to B, if you were to add those together, then you would have the entire area of both regions. That's the additive property, and it probably makes good common sense that that would be the case. Let's take a look at an example. Example 1 says, find the area under the graph from -4 to 5, and we have two functions here. The first function is a constant function, y is equal to 9, but we're on the constant function only for values of x less than 3. Once we are greater than or equal to 3, then we change functions and we end up on y equals x squared. And we will pause momentarily while the computer regains its composure. Hopefully that won't take much longer. Y is equal to x squared. This is a piecewise defined function, and they want us to find the area from -4 to 5. Well, this is going to cause us to use two different functions, right? Because the functions change. In other words, in order to find the area from -4 to 3, we will have to integrate according to the function y is 9. And then to get this area, we will have to switch functions and integrate from 3 to 5. And you'll notice that from -4 to 3, they're doing exactly that, right? They're integrating 9 dx, but then from 3 to 5, they're integrating x squared dx because those are two different functions. And the rest of it is just the same thing we've been doing. The integral of 9 ends up being 9x, and they're evaluating from -4 to 3. There we have the bounds. And then when they integrate from 3 to 5, the integral of x squared is x cubed over 3. And again, they're going from 3 to 5. And then it's just the exact same thing we did before. We plug in the upper bounds, and then we subtract the lower bounds. We do that for both of these functions. And then once we combine them, we can see that the area under the curve is actually 95 2/3 square units. Excuse me. Example 2. Example 2, we're integrating from 0 to 3. And technically, we have two functions here because of the absolute value sign. Let me give you an example. Suppose we were going to graph y is equal to the absolute value of x. We'll just start off with something simpler. Y is equal to the absolute value of x is actually two functions, because if x is negative, for example, -1, the absolute value would be +1. And then if x is -2, the absolute value would be +2. And of course, the absolute value of 0 would be 0. That would be here. And the absolute value of 1, of +1, would be +1. And then the absolute value of 2 would be +2. And notice that when we graph the absolute value function, it looks like a V shape. In other words, those are two separate lines. Those are two separate functions. So anytime we have absolute value, we probably have multiple functions there. It says in the solution that the graph of the absolute value of 1 minus x squared is the graph of 1 minus x squared, where any portion of the graph below the x-axis, in other words, where y is less than 0, is reflected above the x-axis. We see that y is negative between negative, if x is less than -1, and x is greater than 1. In other words, if you look in this region here, all of the y values are negative, and all of the y values here are negative up here. For example, if y happens to be, let's say, -4 at this point, if we take the absolute value, it would project or reflect that point here. Same thing from 1 to infinity. We have negative values, but if we take the absolute value of those negative values, we would get this part of the graph, right? We would have positive points. And then, of course, this piece here doesn't change because it's already positive. All of those points already have positive y values. And hence, we have this graph that looks very different. We would have to integrate from 0 to 3. If we go from 0 to 3, we actually have two different functions. Here is the domain 0 to 3, and we're trying to find the area under the curve, basically. And that means I'm looking for this area here. And then I'm looking for the area all the way over to x is equal to 3, which is going to be this area here. And since we have two different functions, we end up having to break this up into two different parts. In other words, to go from 0 to 3, first we have to go from 0 to 1. That takes care of this function here. And then we have to go from 1 to 3. Once we integrate both of those separately, we can see that the combined area is actually 22/3. Okay, let's take a look at Theorem 6. Theorem 6 says to let f and g be continuous functions where f of x is greater than g of x over a closed interval a, b. Notice that our interval is from a to b, and it says that f of x is greater than g of x. Well, notice that from a to b, f of x is indeed greater than g of x, right? Those y values are higher on f of x than they are for g of x. So what are they trying to say in this theorem? They're trying to say that if you have a situation like this and you're looking for the area between two functions, that would be all of this area here, all you do is you take the area of the entire thing, which means you go from the bottom all the way to the top. First you calculate that, and then you subtract out all of this down here. And then what's left is the area you're looking for, right? It would be this region here. And that's exactly what this is saying. The area of the region between the two curves, between a and b, is the integral of the upper function minus the lower function. So let's take a look at example 3. Example 3, find the area of the region bounded by the two graphs. The first one is a line of slope 2. The second one is a quadratic. And if we look at the pictures here, we can see that f of x is greater than g of x because it's above, right? The function in blue is above the function in red. And we want to find the area bounded by the graphs. Well, they're bounded by two values. X is 0 here, and X is 2 here. So how would we find the area in between? Well, if I put a little rectangle here, and I want to know the area of this little rectangle, I would need to know, let me enlarge that little rectangle. Let me put it over here for a second. Now, the difference, the base here on the bottom, it's very small, so I'm going to call it dx, which means a very small slice of x. And the height of the rectangle is going to be the upper function minus the lower. The f of x touches the top, and the g of x touches the bottom. So the height of this rectangle is going to be 2x plus 1 minus the lower function, which is x squared plus 1. Okay. Isn't it true that to find the area of this rectangle here, I would just multiply this value times this value, because the area of a rectangle is base times height? Now I could simplify this. I could clear the parentheses, and I could call this negative x squared. And then I would do plus 2x. And of course, I have a 1 here minus this 1 here, which leaves me negative x squared plus 2x. And as you can see, that's what they will end up integrating. Let me turn the page here. And this is pretty much what I wrote previously. They're integrating as x goes from 0 to 2, 2x minus x squared. That is the upper function minus the lower. And the rest of it is nothing new, right? They just go through the motions to integrate. They plug in the upper and lower bounds, and they figure out that the area between those two curves is 4/3. Let's look at an example where we actually apply this concept. Example 4 talks about emission control. A college student develops an engine that is believed to meet all state standards for emission control. The new engine's rate of emission is given by this formula here, where E of t is the emissions in billions of particles per year at time t, and t is in years. Suppose the emission rate of a conventional engine is given by C of t is equal to 9 plus t squared. So we have two engines here. The first engine they talk about is the one created by the college student, and then they have a conventional engine. That means it's a popular engine that's used, and they want to try to figure out the difference between the two. Well, first it says, where are the 2 points going to be, where are the two graphs going to touch? Well, if we look here, we can solve for x and figure out that these graphs actually touch when t is equal to 3. How would they do that? You would set 9 plus t squared, set that equal to 2t squared, and you solve, and you get t is equal to 3. Of course, we can't use the negative 3 because we're talking about time, and time is always greater than or equal to 0. So how do they figure out the difference between the two? How do they figure out this area here? Well, if you could envision a rectangle here, Wouldn't the height of the rectangle be the upper function minus the lower? The upper function minus the lower. And then, of course, once we do that, we can integrate this from 0 to 3. And again, they chose 3 because that's where the graphs touch. And they just integrate it, and they come to the conclusion that the answer is 18. And let's interpret what they found. It says over a 3-year period, because we went from 0 to 3, over a 3-year period, the student's engine reduced emissions by 18 billion particles. Okay. So that takes care of example 4.
I'll go to channel 5, please.
Okay, so let's take a look at average rate of continuous function, of a continuous function. We really do not do a lot with this in applied calculus, but I do want to talk about it because I hope that once you see how to calculate it, that it does make sense to you. And I'm going to go straight to the definition because I do think that all of the wording on this page is a bit much for students who are just trying to get to the important things here that we're looking to analyze. We're going to do away with all the discussion. But the definition says that for f, a continuous function over ab, the average value is given by the integral divided by b minus a. So let me just sort of describe what they're saying above and try to make it a little simpler, I guess. We've got, let's say we have an integral, and we evaluate this integral from, let's say, 0 to 2. And suppose we calculate the integral from 0 to 2, and we realize that the area under here is, I'll just make up something. Let's say the area is 15. That if we were to, let me try to get a color here I like, I can. If we were to take a rectangle that has a base of 2, and we were to go up 7.5, then we would have created a rectangle that has an area in blue that is actually equal to the area in red. Now, this is actually a very useful concept if you take more advanced calculus. But for this class, just know how to calculate the average value on a closed interval from A to B. All you do is take the integral, and then you divide by the difference between B and A. And we'll look at an example here. This one is probably a little clearer. It's definitely more drawn to scale than the one I just did, but it's the same concept. Here they are looking at y is equal to x squared, which is a parabola. We have that graph below. And we're going from 0 to 2. And once they integrate from 0 to 2, they realize that the area divided by 2 minus 0, they realize that the area, or the average value actually, is 1 1/3. So notice that they go up 1 1/3, and then they can create this typical rectangle here that has an area that is actually equal to the original area that they calculated, which is all under here. And that's really all it is. And the final thing in this two major details here, we'll just go straight to example 7. It says the weekly revenue in thousands of dollars of trucks rentals, X weeks from the start of the 0, because that's the lowest amount of time you can have, from 0 up to 0 plus 3, and then they just take the integral and multiply by 1/3. And that gives you, and that takes care of 4.4. Okay, I apologize for the delay, but my computer really has trouble with carrying the weight of the Zoom memory plus the textbook memory. So here we are back with integration techniques involving substitution. And substitution is going to bring back the, I hope, fond memories of the chain rule. I say that sort of tongue in cheek. But if you look at parts A, B, and C, you will notice that we have, as our base in part A, we have a u raised to a power of c. And if you look at part C, it says the integral of du over u is the natural log of the absolute value of u plus c. And of course, if u is greater, let's look at example number 1. Part A. Part A says find dy for each function. Okay, so basically, they're just going to start off with some basic review here. If y is equal to x to the power of 3, then the derivative of y with respect to x is 3x squared. We learned that early on in the semester. And if you look at part B, we have x to the power of 2/3. And if we want the derivative, that's just going to, let's go down and look at part D. Since dy over dx is equal to 2x e to the x squared, then that means that dy is going to equal 2x e to the x squared dx. So far, nothing new, right? We learned it's been easy to integrate. But this is an entire function that's not an x, right? It's x cubed plus 1. This is a function raised to a located part of the problem, and usually it's going to be in parentheses, and it's going to be raised to some large power. So that leads me to believe that I need to let u equal x cubed plus 1. And notice, if u is equal to x cubed plus 1, then du has to be 3x squared dx. Now, why is that? Well, think back to example 1. Is it not true that if u is equal to x cubed plus 1, if we took the derivative of u with respect to x, is it not true that we would claim that that derivative is 3x squared? And again, if we put a 1 here and cross multiply, then dy times 1 would be dy, and dy would equal 3x squared dx. So, I'm sorry, that's du. I'm sorry, my handwriting fooled me there. So du would equal 3x squared dx. So why would I use this? Why would I use substitution? Well, notice what happens when you let u equal x cubed plus 1 and du is 3x squared. You would then have a u to the power of 10, in this case, times the derivative of u. In other words, you would have the integral of u to the power of r du. And we know from part A, your answer is, anytime the problem is presented in terms of x, you need to give it back in terms of x. So whatever variable they spit out at the beginning is the variable. Okay. So hopefully that wasn't a big surprise that the derivative actually took them back to the original function. Let's look at example 2. If you look at example 2, I would say this appears to be more complex because it has two terms. So I would say let u equal 1 plus x squared. And if u is equal to 1 plus x squared, then du is going to be 2x dx. And this, then we just use the reverse substitution by calling u 1 plus x squared, and we are finished with that problem. The last one I want to talk about is example 6. Here, I hate to give you a sort of a rule in quotes, but usually whatever this is here, as the exponent for u is going, for e is going to be your u value. And that's exactly the case here. In other words, let u equal x squared, which is what they did. And then they took the derivative of u and realized that the derivative of u is 2x. So du would be 2x dx. But I don't have the 2x dx. All I have is x dx. So here's what we do. We put a 2 here because we have to have 2. If you put a 2 there, you can balance the entire thing back out by dividing by 2 or multiplying by 1/2. So we introduce a 2 and then we take it back out. That doesn't change the answer. This function can have negative y values. This is a line of slope 6. Putting a 2 there and taking the 2 back out. And once they integrated, this was their answer. I want to show you a few problems on this page just to sort of let you know how you would proceed with the substitution. I would let u equal x squared minus 7. And if u is x squared minus 7, then du is 2x, which is already there, 2x dx. And you could just integrate that now as u to the power of 6 du, which is going to be u to the power of 7 over 7. And then you would just substitute the x squared minus 7 in place of u. If you look at 2, this is going to be our u. And then we have t cubed here. With respect to t. And we're just taking the indefinite integral here. Now we could let u equal 3t to the power of 4 plus 2, and that would make du 12t to the power of 3. Well, I would have to put the 12 here, right, in order to have 12t to the power of 3, but then I would have to multiply by 1/12 on the outside. So now I have 1/12 the integral of u du. And of course, that would be u squared over 2 plus c. Another way you could do this problem is to simply go back, and if you can do this, that's great. You could rewrite, and if you let x to the power of 4 plus x cubed plus x squared, if you let that be u, then the derivative would be 4x cubed plus 3x squared plus 2, which happens to be all of this here. So this would be actually, 27 is actually easier than I thought. It's actually going to be the integral of u to the power of 7 du. And it's an indefinite integral. It's an indefinite integral, so that's going to be u to the power of 8 over 8 plus c. And now the only thing left to do to complete this problem is to just go back and substitute in x to the power of 4 plus x cubed plus x squared in for u, and then you're done. So we have just finished up section 4.5, and this is actually the last lecture of new material for this semester. So go ahead and try to get started on problems in 4.4 and 4.5. I will attach some supplementary videos as well, because I know that I'm going to post 2 exam review videos that will be very good reviews for the upcoming exam, which will be cumulative. But if you can understand everything in the exam review videos, you should be in pretty good shape. Thank you.